Welcome back, Frank and friends. I'm Greg Smith, aka Dr. Francintosh, and today we have the offline client. Now, if you remember from last time, we had the offline puck. This was a device that was a file server that you carried around in your pocket, and it was designed to serve up files and be a compute server. Today, what we're going to be doing is controlling that as an MP3 player with a dumb terminal, and this is a handheld device that I created from a Raspberry Pi Pico, and it wirelessly commands the offline puck to play songs and change volume and so on. So as always, please don't like this video, don't subscribe to my channel, don't click up there or over there. Your time is precious. Please don't waste it on anything I'm doing. But as always, thank you so much for spending part of your time with me. And now let's get started. Conceptually, the controller is very simple. We have the Raspberry Pi Pico W at the center and a 16:2 alphanumeric display from Adafruit on the top. And then we have 6 buttons as a sort of a D-pad controller and a reset button. So from the hardware point of view, this is actually pretty straightforward. So the display is not a typical interface with, say, I2C or SPI. We're sending half a byte at a time or a nibble at a time. We set D4 through D7 to whatever value we want to send. Then we strobe the E pin. Now, if we wanted to send data, we would pull RS high. And then if we wanted to send commands, we'd send RS low. And then the commands would be strobed along the data pins. Okay, let's look at the code. Now, for the Raspberry Pi Pico, I opted to go with the C programming language. It's the most powerful. This very conceivably could have been written in Python, but I'm not sure about the performance in that case. So C is always my go-to. So let's take a look at the main program. Pretty much we do a bunch of initialization, then we loop forever. And while we're looping forever, we're looking for key presses. If there is a key press, we process it. If there's not a key press, we check to see if things have timed out. If they've timed out, then we go and we hit the service and ask the MPC service, how are you doing? Get some status. And then update the display if the status has been updated. If we hit a key press, each key press corresponds to a hit on the MPC service. That then responds with a status that we then update the display. So that's constantly what we're doing, just in a big loop, looking for a key press, looking for timeouts. If either of those things happen, we hit the service and get status and then display it. Oh, and by the way, every project has a health blinker. So we have an LED light that blinks to let us know that everything is happy and healthy. Let's take a look at the code. Not much to see here. This is all initialization. Up here at the top, we initiate a standard I/O. Then we update the keypad, update the LCD, print something on the LCD, which is offline client app starting. Then we initialize the Wi-Fi. So here we have the first call we make to the MPC server. We're actually doing an initialization, so we have to update the client with information, including the IP address and the port that we're going to hit. I don't know if I mentioned this before, domain name service resolution on the Pico doesn't work so well. So we're just using IP addresses. Then we initialize our blinking LED. Then we do our first call to the MPC service by calling MPC status. This will send a request for status to the service. It responds with a text string that then gets parsed, and that's what MPC parse status does. And then we use that updated status to update our player object, which keeps the current state of the MPC player. And then finally down here, we take whatever is in the player object and we send it to the 2-line display. Now we're going to enter the big loop. First thing we want to do is determine the last time that things were updated to see if we've timed out. So the first thing we do at the top of the loop is update the blinker. Then we update the display with whatever is the current information in the MPC player. Now, if we've timed out, and in this case, we're hardwired to time out every 5 seconds, we update the last update, call MPC status to get the current status, call MPC parse status to update the player, and then when we get all the way back down to the bottom and come all the way back up to the top, we'll call update display with whatever's in the player object. So we check to see if a key has been read, and if it's not none, that means the key has been pressed. We record that key for the next iteration. Then on the next iteration, if the previous key that was pressed, because then we know that the key has been released and we need to process it. If we hit the back key, then we get an MPC status. If we hit the left key, we go to the previous entry in our playlist. So that actually sends a request over to the MPC service asking it to go back one. And of course, every time we make a request, we get status back, and so we have to process that status. If it's an up key, we want to increase the volume, so we take the current volume, add 10 to it, and then we send the MPC volume request to the MPC service, and then parse the status request that comes back. Likewise, hit the down arrow. That means we want to decrement the volume by 10, and then we send that volume request over. If it's the right key, that means we want to go to the next song in the playlist. We hit the service with MPC next, and then parse the status when it comes back. And of course, if we hit the select key, it's going to ask for the playlist. It'll send the playlist back, and then we'll parse and display the playlist. So that's the entire process. So let's take a deeper dive and take a look at the MPC status command. So you'll see here that MPC status is pretty straightforward. In fact, all of these MPC commands are very straightforward. So we do an MPC call with the name of the command and any parameters or arguments that it takes. So to do a play, we just send the play to MPC. And then down here for volume, we send volume plus the volume. So let's go take a look at what MPC call looks like. Here is the format string that we pass to MPC. We want this information in the status every time we come back. And that's going to be the album and the artist and the title separated by dashes. Then down here, we are actually constructing the URL that we're going to use to send our command to the MPC service. Then we call our HTTP GET, which just initializes a request to the service. And then we have to do an HTTP wait, which waits for the response to come back. And then finally, we print the buffer out. So that is all that the call does. It takes the command and the arguments, creates the URL string, and then sends it over to the MPC service. And when it comes back, that buffer, whatever is in it, is our status. And then we'll process that status when it comes back. Now, back in our main code, whenever we make a call to the remote service, to the MPC service, we get text that comes back that is our status. And now we have to parse that text. So let's take a look at that. So the first step is to call the parse status. Now this is what our response from the HTTP service or HTTP GET returns. And as part of the standard out, we'll get the name of the album, the name of the artist, and the name of the song. And then within square brackets, the current state of the player, whether it's playing or stopped. And here is the song that's playing, the song number in the playlist, and the number of items in the playlist. This is how long the song has been playing in minutes and seconds. And this is the current length of this current track in minutes and seconds. This is how many percentage points we're into the track. This is the current volume. And then other stateful information like whether repeat is turned off, whether random play is turned off, single is turned off, and whether we're in consume mode or not. If there was an error, it would show up in this string, the standard error string. So let's take a look at what it takes to actually parse that. Now we're going to parse the standard out. So we search for standard out. Once we've got the standard out string, we look to parse it. So we start by string tokening it against the backslash character. So every place it sees a backslash, which is essentially where new lines are. So for each token, each line in the text, we're going to start processing it. If we ever get to a right curly brace, we know we're at the end. So we look at the token, and if the token is a left square bracket, we know that that's playing or stopped. So that's the playing line. If it's the word volume, we know we're getting the volume back. Otherwise, it's going to be the name of the song that we're playing. And so we'll want to parse each of those in turn. We dump this all out onto the standard output. So that's the parser. Now notice here that when we call MPC parse status 2, that we're passing in the address of the player, but also of player 2. So this is what in graphics terms would be called double buffering. The main object here is the current state, and then player 2 is the new state. So when we call MPC parse 2, we get the current state of the player, and we get a buffer where we can put in the new state, the state that is coming back from the status. So we check to see if the current player title is different from the player 2 title. So that means that the status that we got back has the title of the song or the artist or the album. Has any of that changed? If it has, then we need to update the player state. Otherwise, we need to update the volume controls. So if the title of the song hasn't changed, we're just going to automatically update the volume. And that's all the news that's fit to print about the main code. Now let's take a quick look at the display, and also let's take a look at how we manage HTTP requests. So here's our commands, things like clear the screen, set the cursor home. Then down here are some flags for orientation, whether we're sending text left to right or right to left. Display control flags, display on or off, which is for the LCD, cursor on or off, and then of course blink on or off is actually the LCD backlight on or off. Now these are control flags for the onboard controller. We have to tell it that we're in 4-bit mode, that we've got a display with 2 lines, and that it's 5x8 dots. When we send data, we have to let it know that the data is available on the data bus, and so we pulse the E pin or the enable pin. Now we are working with 4-bit nibbles instead of a 8-bit byte, so we are only sending half a byte at a time, which means we have to send 2 nibbles every time we send data. Now we could have wired this for 8-bit mode, but 4 more wires, 4 fewer GPIO pins, so doing 4-bit nibbles is just fine. Now to send a byte, there are two types of byte to send. One is data, or if it's not data, then it's a command. And so if you send a 1, then you're in data mode, and at that point you want to take the RS pen and raise it high. Otherwise you're in command mode and you want to send the RS pen low. And then you send the first half of the byte, and then you send the second half of the byte. Now if you want to command the LCD, this is a convenience function. You would send the byte that you've got, plus you'd set RS pin to false or low. And if you're sending data, the opposite. It's to send a byte and with the RS pin high. Now initialization, first we initialize our GPIO pins, set the RS and enable pins low, and then down here as a way of handshaking, we send a hex 03 3 times. Now we go into 4-bit mode, 2 lines and 5x8 pixels. We're going to turn the display and clear the LCD. And then finally, tell it that we're going from left to right with no shifts. If you want to set the cursor, you can specify the row and column, and then down here you can put a single character or a single string. And of course, if you want to send text to the 2 lines of the display, then you can use LCD print 2. Finally, to turn the display on, you have the LCD display function, turn the cursor on or off, turn on or off the backlight. Okay, so now let's look at the code that drives the keypad. Here's the init function for the keypad. Nothing really fancy here. We've got a bunch of constants for the pins that are assigned to the keypad. We initialize the keypad, set their directions to GPIO in, and give them all pull-up resistors. And then we have a method that we'll call keypad read, and it just checks each of the keys in the keypad one at a time and returns a key if it's been pressed. Now, one thing to note here is that apparently some keys are more important than others. For example, the key back, right? If I hit the back key and at the same time as I'm hitting the left key, it will return key back, not key left. And this is true for all of these keys. Now, in our case, that's not that important. We don't need N key rollover or anything like that. So, we're pretty much just pressing one key at a time, but it is noteworthy that, there is a priority to the keys, and basically the order in which they're listed here is that priority. So now let's take a look at the HTTP get function. This is a pseudo synchronous asynchronous call. The way we initiate the calls, we do a HTTP get with a opaque handle to some stateful information, along with the host name, the port, the path of the URL of the resource we're going to hit, and then a buffer to be filled with the response and the maximum number of bytes that buffer can hold. Once we make that call, we don't actually get the response back immediately. This is just queuing the call up, and then once the call is made and it returns, then we can get the data. First, we have to call HTTP wait. This will wait forever until the get completes, and then once that's done, we can access the buffer. So HTTP get first tries to convert the host name into an IP address. And if it's not in the form of an IP address, then we go on to the next step, which is to do DNS get host by name. Now, DNS get host by name doesn't work well on the Pico. We have to assign a DNS server. It doesn't have one. So usually what happens is we pass the IP address in, and this is satisfied immediately. Now, if we did call DNS get host by name, we would supply a callback so that once the host was identified, it would do that bit of code. And what we're essentially doing is chaining. We do a get host by name, then we do a TCP connect, then we do a send a get, and when that responds back, we get the buffer. So there's a whole chain of callbacks, and these callbacks are defined in our code. Now I have my static functions, my local functions start with an underscore just so that we know by looking at it that it's a local function. All of that to say that we almost never get down this far in the code, because what we do are we are passing in an IP address. It resolves it to an IP number and then immediately calls DNS found directly. So once it's found the IP address, it calls this bit of code and then does a TCP new IP type. And you can see here that the stateful information in the HTTP header file, there's a TCP process control block that is keeping track of all the things having to do with TCP. And that's what we're passing into the Raspberry Pi's TCP code. Other things that are kept in here are the IP address, whether or not the request is complete, whether or not we connected, the host name we're trying to connect to, the path of the URL resource that we're trying to get, the port of the IP address, pointer to the buffer that we're going to fill, the maximum size of that buffer, and because we may have to make multiple calls, the length of the buffer. So all of that inside of our HTTP client opaque handle. So we get a new type and fill it in, fill in the blanks in our TCP header, and then initialize the Raspberry Pi's Wi-Fi and make our TCP connect. So we're trying to connect to our remote host, and then if that does connect, or when it does connect, it'll call this callback, which is HTTP connected. Of course, if anything goes wrong, we got an error code back, and we complete the request and then close our connection. So once we're connected, we go into this section of code. So the first thing it does is construct our GET request, which includes our host name and the path of our request. And then we, again, check on our Wi-Fi to make sure it's available. And then we do a TCP write, which has the control block on our request, the size of the request. And if anything goes wrong, we return that result. Otherwise, we call TCP output. And of course, if anything went wrong, then we get out, and then finally we get back. Now, by the time we get to this piece of code, the complete request has been made. The buffer is now full with whatever the server wanted to send back to us. If there were errors, they would have been handled by these HTTP result. And as you can see here, it got a complete request and it closes the socket. So popping all the way back out, once this HTTP GET has been made, we don't get the data immediately. As I mentioned, the Raspberry Pi Pico's TCP code is handling this in the background. So it's in the background waiting for the response. We could go ahead and do other processing. However, in the case of this device, we do an HTTP wait. And all that really does is it loops forever until the HTTP client status information that we, status buffer, has a complete. So we're in a hard loop waiting for the request to complete. And if it times out after a certain amount of time, and I think it's half a second, it will actually close the connection and return an error. However, once it does complete, then it will put a null terminator on the buffer. This is a convenience. Under normal circumstances, we wouldn't do this, but we know that this is a string coming back from our server, so we null terminate it so that it's usable on the client side, and then close the TCP connection and return true. And that's pretty much it. So that's the first offline AF dumb terminal. So as you can see, it is pretty clunky, kind of not the sort of thing you would want to carry around in your pocket, although I did power it with a power brick in order to make it portable. And as much fun as it was to build and program, this is not the end state that I was hoping for with respect to the offline dumb terminal. So I am investing in the M5 stick. So this is a little device. It's got an ESP32 in it, so I'll be expanding my horizons by working with ESP32. It's got a 1.2-inch OLED display, full color, and 3 buttons. I believe it also has a small speaker and a microphone. So it also has a wrist strap so that I can wear it like a watch, and it has an accelerometer, so I should be able to tell when I've raised my arm to turn the display on and off. May even be able to do some hand gestures. So this is looking like a very interesting ESP32 to expand my horizons. As always, please don't like this video, don't subscribe to my channel, don't click up there or over there. Your time is precious. We have so little of it, but thank you so much for spending part of it with me, and I'll see you next time on Dr. Francintosh.